Hey, this is Mr. Ward, and I'm going to talk about some more problems from chapter 10.3 on arcs and chords and central angles. I'm going to look at number 16 right now. So the first thing I want to do is simply identify some information on this one. We have been told that this is circle O, so O is the center of the circle. We've been told that OP, this segment here, is perpendicular to AC. We're also told that OQ is perpendicular to BD. We're told that OP and OQ are congruent, so I'm going to label that with green. And we're asked to prove that AB, arc AB, is congruent to arc CD. So I want you to consider first, what do we know about arc AC and arc BD? Because that's going to help you. And that's where I would ask you to pause and continue without my commentary for a little bit. And I hope you paused and now you're back and you have figured something out, or you have questions, or you're stuck. I'm going to go ahead and identify a few things. So one thing that we know, because OP and OQ are congruent, which means O is equidistant to point P and point Q. It's also equidistant to chord AC and chord BD. And we know that the distance is the distance to chord AC, and the distance to chord BD is these segments, OP and OQ, because they're perpendicular. We can say that this chord is congruent to this chord. And if that's true, then we can further say that chord AC, that was terribly done. Let's try that again. Chord AC, much better, is congruent to chord BD. Okay, so we have that information. Well, let's take a look at a little tiny bit of overlap that exists. They both share BC as an arc. And if they share BC, we can just subtract BC from both of these congruent things and get congruent differences. So we will have a way to prove arc AB, since AC and BD are congruent. Arcs AB and CD are congruent because we can subtract this same thing from each of them, and by subtraction, they're congruent. Now let's take a look at number 17. 17 tells us we've got circles B and D are congruent. We also are told that arc AE is congruent to arc CE. So let's label some of that information. So we know arc AE is congruent to arc CE. Okay. And I'm going to ask you to consider, what does it tell us about some of the segments here if the two circles are congruent? We need to prove now that ABCD, that quadrilateral, is a parallelogram. So let's see what we can do with that. I'm going to ask you to pause and think about it yourself. Okay, assuming you pause and you're back, I'm going to go ahead and label some things we know. We know that the radii of these are congruent. So those two are congruent, and I could also label BE and ED as congruent. Okay. Now, there's more things that we can figure out. So one thing you want to think about is, how do you prove a parallelogram? Well, we have these sides are part of this quadrilateral, and we have CD and AB are congruent. So they're opposite sides. So one way to prove this is if you can prove two pairs of opposite sides are congruent, then you'll be able to prove that it's a parallelogram. So there's actually a path to doing that. There's also a path to proving that AB and CD are parallel. So if they're parallel and congruent, then it's a parallelogram. I'll first explore that because that's a pretty simple one. So if, let's think about this. We know arc EC is congruent to arc AE. And that means that this angle, EDC, has to be congruent. I'll go ahead and use blue again. This is congruent to this angle because the arcs are congruent. So the central angles have to be congruent. That's one of the theorems that we've been exploring in this section. Now, notice that these could be considered alternate interior angles with BD being a transversal, which would force AB and CD to be parallel. So now we have opposite sides that are congruent and parallel. That proves that it's a parallelogram. Now, there's other things that we can prove, though. Since this angle and this angle these angles are congruent, and this side here is congruent to this side, we can also say, of course, that BD is itself, and then we can prove by side angle side that triangle ABD is congruent to triangle CDB. And then we could go ahead and use Kappa-Kadaka to prove that AD is congruent to CB. And now you have two pairs of congruent sides. That does the job as well. And you'd also have another pair of angles that are congruent because of Kappa-Kadaka. So you have, not only are they congruent, they're parallel. This is a parallelogram all over the place. All right, let's take a look at 18. We're asked, we have a polygon inscribed in a circle, and if all the vertices lie on the circle, okay, let me restate that. A polygon is inscribed in a circle if all the vertices lie on the circle. So we want to find the measure of the arc cut off by a side of each of these regularly inscribed polygons. So this one, of course, is a hexagon, but we could also have done a pentagon or an octagon. And what you want to do is think about the central angles that would be produced here. Now, all these central angles are going to be the same. So in this hexagon, if you know that what the interior these angles are in a hexagon, and you can work that out using some formulas we dealt with in the past, the total degrees inside a hexagon are going to be 180, well, of any polygon, are going to be 180 times the number of sides minus 2. Okay, that means that the degrees of a hexagon are going to be 180 times 6 minus 2, or 180 times 4, which is 720 degrees. Wow, that was pretty cool. Let's try that again. 720 degrees, and we divide 720 by 6 to get all of those interior angles, and we get 120. Okay, so that's 120 there. And since it's a regular hexagon, that means that this angle is 60, this angle is 60, so this angle is 60, and then this angle is also 60. So we can use those interior angles to find out the central angles. So the measure of the arc is going to be the same as the central angle, and that central angle is 60 degrees. So the arc is 60 degrees for the hexagon. So 60. For the pentagon, instead of 720, instead of 6 minus 2, it's going to be 5 minus 2. It's 180 times 3, which is going to be 540 degrees. So I'm just going to note that the overall degrees is 180 times 3, so that's 540. And then we divide that by 5, and each of the interior angles would be 108. And then half of them would be, half of 108 is 54. So you'd have two base angles that are 54, and then you could work out the central angle from what's left of 180. And we can do the same thing on the octagon. I'm not going to solve that. I'm going to let you work that out yourself. Now I'm going to talk about 19 and 20. So number 19, we are given a circle P. So P is the center of the circle. We're told C is the midpoint of arc AB. We're told D is the midpoint of AB. And we're trying to prove that CD passes through P. Okay, well, remind yourself what PB and PA would be, and maybe draw those. Think about the perpendicular bisector theorems from way back in chapter 4. Pause the video and see what you can come up with. You're going to need to draw some lines. I assume you have paused the video and you are back. And I'm going to go ahead and note that P is equidistant to A and B. So P has to lie on the perpendicular bisector. Okay, now we also know that D is equidistant to A and B as well. So that tells us this. Okay, so D is equidistant. So D and P are definitely part of the perpendicular bisector, but we really have to deal with the fact that we don't know if C lies on the perpendicular bisector before we can say that CD passes through P. So we need to figure out, does CD make a perpendicular? So let's draw some additional segments here. So I need to use a different color for that. Let's try green. So we're going to draw chords AC and AB. Now, can we prove that those are congruent? Yes, we can. We're going to have to back up, though. We're going to have to prove that triangle ADP, and I'm going to draw this line like that because we haven't confirmed that yet, but we can treat DP as a segment, and we can prove that ADP is congruent to BDP, and that is going to tell us that this angle here is congruent to this angle here. We can prove that by side because the radii are the same. We know AD and BD are the same, and we know that DP would be itself. We haven't yet proven that DP lies on CD as a segment. Okay, but we'll get there. Because we can prove these two angles are congruent, we can prove that arc AC is congruent to arc CB. And if that's true, segment AC is congruent to segment BC. So now I can be comfortable with the fact that I drew those chords. Chord AC and chords BC are congruent because their corresponding arcs are congruent. So I'm comfortable now that AC and BC as chords are congruent. And now I can say, of course, that CD is itself. So I'll use purple for that. CD is itself. So now I can prove that triangle ACD and triangle BCD are congruent by side. I know that C, actually, I didn't even need to do that. I know C is equidistant from A and B. I know D is equidistant from A and B. And I know P is equidistant from A and B. And so I definitely know that CD goes through P because CD is a perpendicular bisector and P lies on the perpendicular bisector. I could probably have done that more efficiently. Let me back up just a little bit to talk about how that could be done really efficiently. We can very easily establish that D lies on the perpendicular bisector. We have to prove this triangle ADP is congruent to BDP to prove that chord AC and chord BC are congruent by proving that the central angles are congruent. In fact, our theorems allow us to prove that if our central angle are congruent, then the chords they intersect are congruent. So we didn't even need the arcs for that. So that would be more efficient. And then once we had proven that the chords are congruent, and we know P is equidistant from A and B, we know that all 3 points are equidistant. So CD is a perpendicular bisector, and P lies on a perpendicular bisector of AB, and we're good. Let's take a look at 20. In 20, we are given circle P is congruent to circle C, and that's going to be very useful to us. And we're also told that BC is congruent to CD. So think about what it means that the circles are congruent, and we're going to try to prove that angle A is congruent to angle E. Okay, so pause the video and see what you can come up with. So let's start by labeling some things. We know that BC and DC are congruent. We also know the circles are congruent, so we can say that PB is congruent to QD because they're radii, and we can also say that QE and PA are congruent because they're radii, and they're radii of congruent circles. And on top of all of that, we could say that by addition of congruent parts, AB and ED are both congruent. Now, it would be useful to find some angles that are congruent at this point. But one idea I've had here, and there are probably a few other approaches one could make, one idea I had was let's draw one more radius, PC and QC, and those are actually going to make one segment, which means that we have some angles right here. That angle and that angle are going to be congruent because they're going to be vertical angles. So now I've drawn that. I already knew that this was congruent, and that tells me that I've got an isosceles triangle here and here, and the angles here are also going to be congruent to those vertical angles. And I think we're done. I'd be curious about what other methods. This chapter, of course, focuses on the congruency of arcs and chords and central angles. I've just done the proof without the use of any of that stuff. So I'd be curious to see what approach. I think that's a simpler proof. I'd be curious to see how you might have used the arcs and chords and so forth. And that's where I'll stop.